This video is about a machine learning project that uses convolutional neural networks to solve a specific image classification problem. I want to show my thought process and progress from the decision to use machine learning, finding the right tools, following a research routine, to finding a suitable solution. The goal of the project was to improve the quality of the images generated by procedural algorithms. The dataset was based on previously generated images and further expanded with photographs and digitally created images for more stable and future-proof results. This project is part of a big abstract image generation project, which is part of an even bigger project, a software system for designing algorithms. One of its main features is the implementation of various approximation and evaluation methods. The first application of it was a subsystem for designing sound processing and sound generation algorithms. After that, I started to develop a subsystem for image and animation generation algorithms. With custom-written software, I'm able to produce, visualize, and store algorithms in an efficient and customizable way, analyze them in detail, while keeping the entire production chain in one application. One of the issues I found more difficult to resolve was the low efficiency of approximation caused by low metric separability. The metrics used a combination of various factors of reference resemblance, constructed in a way to produce images with some characteristics of referenced images, while allowing the results to be as diverse as possible. The problem was a lot of bad images. Although the algorithm construction methods were chosen for algorithms to produce higher quality images on their own, the metrics part could be improved. So I decided to try machine learning with CNNs just to improve my resemblance metrics at first. I've got a mix of the images generated using some reference and downloaded the ResNet50 Matter model to get started. I loaded it into Keras Tensorflow in VS Code with Jupyter extension. I produced embeddings for my images and applied cosine metric to calculate distance to the reference. And it didn't really work. This method couldn't differentiate images any better than my metrics, probably because generated images were all not very close to the reference. Another concern was that this model seemed pretty slow, and it was critical for my application. I still decided to try it in my C# system, so I converted the model to ONNX, loaded it into ml.net, and checked its performance. It was slower than everything else in my process combined, and I needed to run it millions of times continuously. So instead of trying to improve the model, I decided to create a small custom model with a more precise and easy goal of separating bad and good images without any reference, because that was what I really needed at that point. I exported a few thousand marked images from my applications database as a dataset. I tried to set up Keras and TensorFlow for online augmentation, but it was not smooth at all. There were incompatible versions with different workflows, and each of them was lacking something I wanted to use. So I happily switched to PyTorch and decided to use PyTorch Lightning. It allowed me to easily load the dataset, apply augmentation rules, and prepare an initial workflow for training and testing models. I decided to start with binary classification because it could be sufficient for my goals. I chose balanced accuracy for my validation metric. I set up a small custom model based on ONNX layers, trained it, and got around 75% balanced accuracy on the test set, with 90% sensitivity and 60% specificity, where good images were considered positives and bad images negatives. It meant that with this method I could drop 60% of bad images while keeping 90% of good ones. It seemed decent enough for first try, and it worked fast enough on my GPU, so I proceeded to continue. To have a reference model, I took the ResNet50 model previously converted to ONNX. I loaded it into PyTorch, added a linear layer over its vector output, and trained these layers weights on my dataset. It scored 87% balanced accuracy, which was quite a bit better than my own model, but it evaluated images about 40 times slower. At that point, I was able to make a more formal statement of the problem. I wanted to train a model that would not significantly slow down my process and could achieve around 90% balanced accuracy on the appropriate dataset. I also checked that this was about the accuracy with which I could relabel images myself. With all preparation completed, I started solving the problem. I checked that the new custom model was working fine in my C# system. To do this, I again converted it to ONNX, loaded into ML.NET, and did performance testing. I implemented hybrid calculation in ML.NET so it could use either CPU or GPU depending on what is available, and everything seemed fine. I started making a new large and robust dataset. For the good part, I prepared and added copyright-free and my own photographs and 3D images generated with geometry nodes and simulations in Blender. For the bad part, I included random parts of photographs and random noise images. Overall, it was about 8500 images, with approximately 80% bad and 20% good. I further improved the augmentation, and the data provider was also balancing the data to make it 50-50 and keep the loss function simple. I tried a few of the smallest models that made sense for me and wrote a wrapper class that allowed me to change models using a single matrix of layer parameters, such as the number of output channels, kernel size, stride, padding, batch normalization, max pooling, and dropouts. I set up classes and options for other important training techniques, like learning rate monitoring and custom adjustment rules, early stopping, and gradient clipping. Additionally, I added extra labels to my dataset and CSV file for reproducible 5x5 cross-validation. I set up a VS Code SSH workflow to comfortably run training on two computers with GPUs. I profiled all operations for CPU, GPU, and memory efficiency and optimized a few things. In particular, building PyTorch from source for my specific GPUs reduced its memory usage by 30%. At the same time, I tried different models, consecutively changing a few layer parameters while keeping model complexity low enough. After training about 70 models, the balanced accuracy reached 90%. I analyzed how the best models performed on the dataset, and it looked pretty good for me. Their predictions made sense across different types of images. There was no clear best model because of close and variable evaluation results, so I just chose the model that looked nicer for me and switched back to my C# system again to try it. And it didn't go as well as I expected. The number of good images produced per hour increased, but I still had to manually remove up to 75% of the images that were obviously bad in the first stage of post-processing. However, the source of the issue was easy to find. Since the production of bad images is much easier than finding good ones, my process just adapted to trick the CNN evaluation by inventing more bad images that could pass its test. The solution was clear as well. I simply produced more images that were bad but tricked the CNN and added them to the dataset. After finding and fixing an obscure mistake with the export of the images, I also decided to make another round of dataset cleanup, mainly to remove images with uncertain classes. Additionally, I found and resolved the augmentation resembling issue that led to aliasing artifacts affecting image evaluation. I tried a few of the best models again on the new dataset with cross-validation, and my previously chosen model was performing well, so I retrained it with full new dataset, converted, enabled in ML.NET, and ran a session. The success rate for the first stage of my process went from 25% up to 50% with the settings that I tried, and the images I still needed to eliminate were mostly not obviously bad but rather uncertain. The improvement for the stage was massive, and I decided to pause my ML project at that point with that model ready for use, as there were many more things to improve in the overall process.